Okay, so in the last class we talked about the wave function and we said that the probability of finding a system in certain state is given by this. Well, actually, this is a probability density. It's not really probability, but probability density. Now, psi can be a function of variables like distance, or which means x, or time, momenta, things like that. But we're not really right now too much concerned about the variables on which psi is dependent. That certainly will be determined by the type of problem which is at hand. But usually psi is a function of x and t. Anyway, so this is the probability density, and the very first question one can ask is um, how does this probability density evolve in time? So how it changes with time? Well, it may change with time, it may not change with time, but let's assume that we are interested in the question that how does this probability density changes with time? And this problem was handled by Schrodinger, and using analogy between mechanics and optics, he actually came up with an equation which wrote like this: IH bar partial derivative of del over del t psi. Let's write psi as a function of x and t equals minus h square over 2m. Now this is equation, this particular equation is for the assuming that there's a particle which has mass m, and this particle is being enacted by a potential Vx. So like mechanics, we have problems when there's a particle which has a mass, and we solve all sort of problems regarding kinematics of the particle, that how it moves, how it accelerates, and things like that. That's how we start physics, or kinematics, at least at 200 level. And here we have the similar kind of situation. The Schrodinger equation is telling what those three equations tell in kinematics. If you remember that x equals x naught plus vt, x equals x naught plus v naught t plus half at squared, something like that. So we know all this. So here Schrodinger equation is telling how wave functions evolves with time, and actually we can in fact write it a little differently like this. And this h is called the Hamiltonian operator. As you can clearly see, it's actually an operator which is acting on wave function psi. Explicitly, this is okay. And if you have taken a course in classical mechanics, you can actually see that Hamiltonian um, actually sort of gives the energy of a system, and will come to know later that this is sort of equivalent to p square over 2m plus vx, which we all know is the total energy of the system, or the Hamiltonian of the system. Now p in this case is an operator, and we'll talk about that later, but right now this is just for the sake of terminology, that this is how the wave function evolves in time. This is the operator. If you're not comfortable with h, you can just assume this, what we are talking about, and we are certainly aware with these operations. And this is called the time dependent Schrodinger equation. As you can see, there's a time which is playing here. Now it may happen that you may encounter a situation in which the system is actually not changing with time, which simply means that energy or psi xt square does not depend on time. We may have situations like these. For example, in the last class we took the example of a harmonic oscillator being in its ground state, then it's E minus E0. This was the phase function for that particular situation when your system is just in the ground state, which has a fixed energy. Don't worry if you don't understand much of it, we'll certainly talk about this later. For this particular case, energy is a constant, and this psi 0, which we said was a function of something we call it f1x, something like that, did not change with time, so it stayed same with time. And if we have these kind of situation, we can clearly see that this actually starts looking like E psi equals H psi. If you do small calculation, you will find this. H again is the same thing, and this is called time independent Schrodinger equation. Okay, so this is where we start our formal application of of theory in quantum mechanics, and start to develop mathematical tools by which we can solve these kind of equations, and we'll talk about that in the next class.